Chemistry, Science 10. Chemistry Science 10 builds on a lot of the stuff you guys would have looked at in grade 9. We jump right into using the periodic table. You guys would have spent a bunch of time in grade 9 learning about the periodic table. Where did it come from? Where are all the things that are on it? Who is responsible for putting the thing together? We're not going to do any of that in grade 10. You're just going to use it. I'm going to assume that you're comfortable with it. If any of you have your periodic tables left over from grade 9, I know some of the science teachers, not all of us, but some of us, make a big show of the periodic table and then have you color different things and then laminate the thing. If you have that, you hang on to it. You're welcome to use it. Bring it to class. It'll make your life a lot easier. Otherwise, I've got one on the inside front cover of this package, and I've got another one that I'm going to be handing out when we get to reviewing naming of all of these compounds and chemicals. That is shaded a little bit differently, but for now, this is the one that you've got, unless you have that big one. So let's review the things. Chemistry intro. There's a word that's missing here. The word that's missing here is all. All matter is made of what? What's the magic word? All matter is made of blank. All matter has mass. Also has volume. Yes, atoms. All matter is made of atoms. We could talk about, there's smaller things than atoms. We could talk about the smaller blocks. But there is a reason why we focus in on the atom. We like the atom. Why do we like the atom? We like an atom for the second sentence. An atom is the blank unit of an element that still has the same blank properties of that element. It is the smallest unit of an element. Like if you had the carbons, all the carbons, the smallest amount of carbon you could have is a single atom, or an oxygen. The smallest amount of oxygen you could have that you could still call oxygen is a single atom. That's why we like the atom, even though there are smaller particles. We like the atom. It's the smallest unit of an element that still has the same blank properties. What kind of properties do we care about? You would have talked about this in grade 9 as well. Yes, another word for that. Starts with a C. Elements have there are two classes of properties that everything has. One class of property deals with things like color. Another class of property deals with things like conductivity, reactivity. Which of those properties do we care about the most when we're talking about elements? Starts with a C. Sorry? Chemical is the word that we're looking for there. It still has the same chemical properties of that element. And I said it before, we'll look at it here now again. Atoms are not the smallest particle. There are particles that are smaller. Atoms are made up of subatomic particles. How many of them? Which one is it, 2 or 3? It's most of the time it's 3. Sometimes it's 2. Depends on what that atom is doing. But as a general rule, atoms are made of 3 subatomic particles. And they're listed for you right here. We got protons, we got neutrons, we got electrons. What can you tell me about a proton? Who remembers what about protons? It is positively charged. And specifically, it has a charge of what? It is positive, but how much positive charge does each proton have? Yes. Each proton, we say, carries a charge of +1. And there's a complicated reason. Well, it's not a complicated reason. There's a reason for that. Because protons themselves are made up of smaller things. Yes, protons are made up of something called a quark. And those quarks have different charges. And the sum of the charges on those quarks give the proton a charge of +1. Where's it found? Where do you find protons? Within an atom, where do you find a proton? Yes. In the nucleus. So let's draw a little over here on the side. There's my nucleus. Within that nucleus, you're going to have a bunch of positively charged things. Not all of them are going to be positively charged. Let's put 4 of them in there. There's our nucleus. And there is a property of the atoms that protons are equal to. What concept do we say that the protons are equal to when we're talking about atoms? It's in the little diagram there on the right-hand side. Something in here is what the protons are equal to. It's not the ion charge. It is the atomic number. This guy here, when you're looking at the periodic table, tells you how many protons you have. So the protons are equal to the atomic number of an atom. Now, there's a symbol we use when we're talking about protons. I don't want to write the word proton every time. The symbol that we use for a proton is a P with a little plus sign. And protons are one of the 2 particles in an atom that actually give the atom mass. Protons, we say, have a mass of 1. But a mass of 1 what? Because protons are really small. It's not 1 gram. It's not 1, obviously, it's not 1 kilogram. We say protons have, because it's so small, we make up a unit. Does anyone remember the made up unit when we talk about the mass of a proton? I mean, my class would have talked about it briefly. It's not something that you necessarily would remember, though. Protons, we say, have a mass of 1, and then we make up a unit. We call it the atomic mass unit. Whatever it is. I mean, grams are just made up, too. We made up a unit that works. We say the protons have a mass of 1 atomic mass unit. Then we move to the neutrons. Where do you find a neutron? What is special about a neutron? What do you know about neutrons? They're not negative. It's in the name. They're neutrally charged because it's a neutron. And if something is neutrally charged, it has a charge of what? What's the numerical value for a neutral charge? 0. Neutrons are found where? Also in the nucleus. So in these the ones that don't have anything in them, let's put some N's in there. Because the symbol that we use for a neutron is actually the letter N with a 0 up next to it. And the number of neutrons that you have are equal to the atomic mass minus the atomic number. This is true because neutrons also have a mass of 1. And I'm not going to write out atomic mass unit every time because that's a lot to write. We abbreviate it as AMU. So protons and neutrons each have a mass of 1. And when we talk about the mass of an atom, these are the two that carry effectively all the mass. So to find how many neutrons you have in a particular atom, you take a look at the atomic mass, and if all of the mass is protons and neutrons, and the atomic number is the protons, then the neutrons are going to be the atomic mass minus the atomic number. For example, this is titanium. It's got a mass of 47.9 and an atomic number of 22. So if I wanted to find the number of neutrons in titanium, I would take that 47.9 and I would round it. 47.9 rounds to what? You betcha, 48. So that's 48 AMUs. And if I wanted to find the neutrons, I would just take away the 22 protons. 48 minus 22 is 26. And if I've taken out all of the protons, all I have left are neutrons. So this titanium would have 26 neutrons. Good morning, Alex. How are you?
Good, how are you?
Good. How's your long weekend?
Fantastic. You know what? I probably had the least productive day in my life.
Happy for you. I cleaned up more bodily fluids coming out of my sick children than I would have liked yesterday. It's a good time. Yes, but adult children have troubles too.
They sure do. They clean up their own body.
It's true. Okay. That's protons, those neutrons. Let's talk about electrons. Electrons are really, really small. Where are they found? Outside. You betcha. I need a different color. I need blue. Found outside the nucleus. So over here. Or maybe over here. Maybe over here. Maybe over here. Who knows? Somewhere outside. Electrons are so small we don't actually know what they look like. No one's ever seen one. No one will ever see one. We know they behave all sorts of different ways. Sometimes they behave like particles, like a solid object, like a baseball hitting you. Sometimes they behave like waves. Electrons are weird. We don't actually know what they are, but we know they exist because they have to. What's the charge on an electron? What do you remember? Yes, Brooklyn. They are negatively charged. Specifically, how much negative? Every electron has how much negativity? Sorry? It has, one negativity. So each one has a charge of -1. And they're really, really small. If you were in my science class, I would have given you this number last year. If you were in a different science class, perhaps they didn't. Does anyone know or remember the mass of an electron? It's kind of a ridiculous number. Sorry? 4 is part of it. That's okay. I'm not expecting you to. It's 0.0054 AMUs. Why? I don't know. It just is. Even though we don't actually know what it is, even though if we don't know if it's a particle or a wave, we know it has mass. It's measurable. It's very, very small mass, but it's a measurable amount of mass. But it is so small that we effectively ignore it. For example, in this thing that I've drawn right here, this thing has a mass of, well, what is it? It's got 4 protons. So this thing is actually beryllium. 4 protons. The protons tell you what element you have. So atomic number of 4 means that this thing that we've drawn is actually an atom of beryllium. So this thing, this whole atom, the nucleus would have a mass of 8 atomic mass units because there's 1, 2, 3, 4 protons and 1, 2, 3, 4 neutrons. This thing would have a mass of 8. The electrons would be 0.0054 times 4. So the whole mass of this, the nucleus is 8. The whole thing is 8.02. So that 0.02 is such a small part of it that effectively we can ignore it. When you go get your driver's license and if you step on the scale, they're like, yes, you are 80.05 kilograms. Well, let's just call it 80. The electrons offer so little mass that we effectively ignore them. And the number of electrons is equal to the atomic number only in an atom. So atoms are neutrally charged. Atoms are neutrally charged because the definition of an atom is when you have a singular piece of an element where the protons equal the electrons. When this is true, so your positives equal your negatives, when they sum up to 0, that means that you're dealing with an atom of an object. They don't have a positive charge, they don't have a negative charge. When you become charged, then you're no longer an atom, now you're an ion. Ions are atoms that have either lost or gained electrons. The protons can't go anywhere. Protons dictate what kind of element you have. They have to stay. They're in the nucleus, they're bound there. Electrons can come and go. Since electrons are negative, if you lose an electron, the atom becomes? If you lose a negative, how are you charged now? Positively. So the atom becomes positive if you lose an electron. You can think of electrons as a bad mood. If you lose a bad mood, now you've got a better mood. You become positive. In an atom, they do. Charge-wise, they do. But as you start to gain and lose them, now they're no longer balanced. That's where you get that charge. If you gain an electron, the atom becomes what kind of ion? Electrons start to show up. The atom becomes? Did someone say it? I didn't hear it. If you lose electrons, the atom becomes positive. If you gain electrons, it becomes negative. So when you guys were learning about the periodic table last year, you would have looked at three, I guess, families on the periodic table. On the periodic table, I'm going to give you only 2 of those families are labeled. And I'm not talking about the alkali metals or the alkali earth metals, the halogens or the noble gases. I'm talking about like the 3 big divisions on the periodic table. They're split by this big black line here. Sometimes it's called the staircase. To the left of that, we get the metals. On the right of that, we get the non-metals, though there are some kind of awkward ones here in the middle that have properties of both. We call those the metalloids. Right now, we don't care about the metalloids. What we care about the metals are the non-metals. All metals become the same kind of ion. All non-metals become the same kind of ion, with a couple exceptions. If you are a metal, all metals do what? With their electrons, do they gain or lose? They all lose electrons. Metals, as a rule, lose electrons to become positive. If you lose electrons, you become positively charged. Non-metals, as a general rule, gain electrons to become negative. Now, this is only true like 90% of the time. If you wanted to force metals to gain electrons, you could. If you wanted to force nonmetals to lose electrons, you could. But as a general rule, this is what they will do naturally on their own. In nature, metals will lose, nonmetals will gain. So for example, lots of you have you're looking at the periodic table in front of you, that's great. Chlorine. Chlorine is what? A metal or a nonmetal? Where is it on the table? There's some tables on the back wall too. There's going to be a table on the front wall, but I haven't put it up yet. Where is chlorine? Is it a metal or a nonmetal? It's a nonmetal. What's the charge on chlorine when it becomes an ion? On your periodic table, if you see just a plus sign or just a dash without a number, that means +1 or -1. So it's just going to be -1, okay? So chlorine as an ion is going to have a -1 charge. So it gains an electron. Put the number in there. Gains 1 electron. So as an ion, chlorine now has how many electrons? Yeah, who said that? Yeah, 18. So if you take a look, so chlorine has the atomic number of what? The atomic number, not the ion charge. The atomic number chlorine is atomic number 17. So when chlorine was an atom, it had 17 electrons. In an atom, the atomic number and the electrons are the same. It had 17, it gained 1 more, and now it's got 18 electrons. Magnesium. Find magnesium, so it'll be on the far left-hand side. If it's on the far left-hand side, what kind of atom is magnesium? It's a metal. It's a metal that you played with in the lab on Friday. When magnesium ionizes, becomes an ion, what does it do? What kind of ion does it form? It's a positive ion, and it has, what's the positive charge on magnesium? It's going to be 2. So magnesium as an ion is a metal with a +2 charge. To become charged by, to gain a charge of +2, what does it have to do? Yep, how many? Loses 2 electrons. So if you have a positive charge, you've lost 2 electrons. How many electrons did magnesium start with before it became an ion? Sorry? 12. So it had 12 electrons. That's the same as the atomic number. It lost, how if I could spell, 2 electrons. So how many electrons does magnesium have as an ion? It's got 10. It had 12. Because the atomic number on magnesium is 12. So as an atom, the electrons are the same as the protons. To become an ion, it became charged, became positively charged, so it lost 2 electrons. 12 minus 2 is 10. They always start with the atomic number's worth of electrons, yeah. Okay, when you're ready, flip the page. What I want you to do, I want to give you 5 or 6 minutes. We'll see how long it takes you to do it. This table. I want you to practice using your periodic table, using the properties we just talked about. I want you to do a few. So each one of these, there's the element name, the atomic number, the ion charge, the number of protons, the number of electrons, the number of neutrons. Use the information that is present to fill in the information that is missing. And the other thing I want you to do in this column right here, where there is nothing written, I want you to tell me whether or not you have an atom or an ion given the information that's present over here. So for example, I'll go through the first one. Potassium, they tell you that the element is potassium, it's got an atomic number of 19. This potassium has a charge of +1. So if it's got a charge of +1, then the potassium has to be what? If it's charged, the potassium is it's an ion. So you've got an ion of potassium over here. The atomic number was 19, so you have 19 protons. If you're positively charged, it means you lost an electron. If you have a charge of +1, it means you lost 1 electron. So then the number of electrons is going to be 1 less than the number of protons. And then to find the neutrons, you take a look at the atomic mass, subtract the atomic number, you get the number of neutrons. In the second row, it says we have phosphorus. The atomic number is 15, and the piece of phosphorus you have has no charge. If the phosphorus has no charge, then what does it have to be, an atom or an ion? It's got to be an atom. Atoms are uncharged, ions are charged. If you're uncharged, then your protons, which was the same as your atomic number, is going to equal the number of electrons, and then you can use the mass to find the neutrons. Does that make sense? I'm not, in this column here where it says ion charge, there's some confusion in my first block. You're not looking for what the table says the charge would be. You're looking to see if the charge is 0, that tells you something about the protons and electrons. If the protons and electrons aren't the same, now you're charged. It means you've got an ion. Give you, I don't know, let's see where you are after 5 minutes. It might take you 10. Which one are you looking at? So, okay, we can do this one together. The atomic number is 3, so what do you have? What? Sorry? Lithium. Cool. Yes. So this was where the confusion came from. So you've got lithium, because you know the atomic number is 3, that tells you on there it's lithium. Now, if lithium ionizes, it's going to have a charge of +1. That's what the periodic table tells you. This table says that the charge on the lithium that you have is 0, which means you don't have an ion of lithium, you have an atom of lithium. That ion charge on the periodic table you have in front of you only is the charge if you have an ion. If you have an atom, the charge is 0. Does that make sense? So that means this value here means that the lithium's an atom. Here, where it says you've got a charge of +2, that means that whatever this is, it's an ion of that element. So elements can show up as either atoms or ions. Play with it. If you need, I'll put on some music and I'll start walking around and giving you a hand if you need it. Boom. So this is what you're looking for. Compare what you got with what I got. Let me know if you've got any questions about any of it. We'll pause the music. There we go. Okay, ladies in the back, phones away. Check your work with mine. Maybe yours wasn't the phone that was out. You're good. Brooklyn wasn't checking. Other Brooklyn wasn't checking. I wasn't mad. You don't have to defend her.
Please excuse this interruption. At this time,
okay.
9 students with last names K through O, and any grade 10, 11, or 12 student who received a vaccination letter at home or who would like to talk to a nurse about a vaccination, please head to the staff room in the Heritage Wing.
Okay, so this is going to be in the video. If you haven't finished it, that's fine. I'll post the videos today during my A block. If you didn't finish it, I want you to finish it. Make sure you've got an understanding of how this works. If you've got questions about this stuff, please ask. Are there any questions about this stuff? We're good? My biggest fear is you'll be just like, oh yeah, I'm going to change this. I'll make this my answer. Without really understanding why. Okay. So let us continue. Bohr models. This is the last thing we're going to look at today, and I'll leave you with some more practice to do for homework. The Bohr model of an atom. The Bohr model is a great model. It's wrong, but it's a great model. In grade 9, you would have been taught 4 models. There would have been the Dalton model, the J.J. Thomson's model, Rutherford's model, and then Bohr's model. Do you recall these guys? Okay. If you were here, you may have learned about these 4 guys. Each of them built on the understanding of what came before to create the model that we have now for the atom. Bohr model, great model. It's wrong, but we use it. So I was making a quick note here. The model is wrong, but it's very useful. Our current model, you can't actually draw on a piece of paper nicely. There's 3D shapes going all sorts of different directions. And so the Bohr model is a really quite a convenient one. But atoms don't actually look like this. They do have a nucleus in the middle. They do have electrons on the outside, but the electrons aren't in nice little concentric circles. They're in kind of ridiculous cloud shapes that are, some look like teardrops, some look like donuts, some just look like balls. It's weird. But Bohr diagrams are useful. They use something called blankety blank to describe the location of electrons around an atom. These rings all have names. 2 words. What is it? Who remembers? What do we call these rings? Starts with an E and an S. The first word is the object that the second word contains. Yep. Electron blankety blanks. Starts with an S. Sorry? No. Some of them are spheres, but they're not all spheres. Okay, I'll give it to you. Electron shells. Each one of these rings is called an electron shell. There's 2 other names for these things too. Those rings are also called orbitals. They're also called, put an or here, energy levels. Because that's what they represent. They represent that there are levels of energy that the electrons jump back and forth between. Each shell can hold a certain number of electrons. Is this blank right here? What do you remember from before it becomes full? First shell holds how many electrons? 2. Next shell holds how many? The second one's 8. The third one is also? The third one's also 8. It is 18. And then that number goes up as you add more rows, or more shells rather. How many each contains is actually found on the periodic table. If you take a look here, the first row of the periodic table has 2 elements. This guy has 1 electron, this guy's got 2 electrons. And then that shell is full, and you move up to the next shell. 1, 2, 3, 4, 5, 6, 7, 8. Fills the shell. The next one. 1, 2, 3, 4, 5, 6, 7, 8. Fills the shell. When you move down a row, you move up a shell. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then you move up a shell. 18 again. Then you move up a shell. The way the periodic table is supposed to be read is that these 3 come first, then these guys, then you jump back here and keep going. So this row actually has not 18, it has 32 elements in it. And this bottom row here also has 32 elements in it. So that means these last 2 energy levels, each of them would be able to hold 32 electrons, which would be an awful lot to draw. We don't draw those. In fact, I'm not going to ask you to draw anything bigger than calcium. So this guy, these how many they contain here is the row of the periodic table. Periodic table. First row has 2 atoms, or 2 elements on it rather. Second one has 8, the third one has 8, the fourth one has 18. However many elements are in that row is how many electrons that shell can hold. When you're drawing Bohr diagrams, and you're going to draw me 10 for homework, when you're drawing these things, or when you're filling up the shells, you start at the top as you're drawing these things, and you move clockwise, generally. Or I'll say typically. There are other times where it's more convenient to go counterclockwise. We'll get there. But generally, you move clockwise, adding electrons like the points on a compass. If you've never used a compass, north is at the top. Then it goes east at the side, and then south at the bottom, west on the left-hand side. You put 1 in each spot. Once a shell is half full, only then do you loop around a second time and begin to pair the electrons. Electrons don't want to be next to each other. Because in the physics section you would have looked at last year, you would have seen that negatively charged objects, if you have 2 negatives, they repel each other. Electrons are all negative. They don't want to be beside each other unless they have to be. So you put 1 in each spot, and then you pair them up afterwards. Flip the page when you're ready. I'm going to get you to draw some Bohr diagrams for practice for me. Here's what I want to see. Every science teacher does this a little bit differently. What I want you guys to do when you're drawing me Bohr diagrams is this. The first thing I want you to do is to determine the number of protons an element has, the number of neutrons the element has, and then write the number of protons and neutrons in the middle of the diagram. This is to mimic the nucleus. So you're going to write P plus equals N0 equals, whatever those numbers are going to go here, and that's going to signify that this is the nucleus of the atom, and then you're going to draw the Bohr diagram around that. The next thing you've got to do is to determine the number of electrons that the atom or ion has, and then begin filling the energy shells. Remember, 2 on the inside, then 8, then 8, then 18. You guys aren't going to be drawing me anything bigger than element number 20. Once a shell is half full, then you start pairing the electrons with each other. There's an extra step for an ion. If I ask you to draw me the Bohr diagram for an ion, once you're done the drawing, you need to put brackets around the diagram and put the ion charge outside the top right corner. I'll do a couple examples for you. First, I'm going to do hydrogen, and I'm going to do an atom of hydrogen. So, how many protons and neutrons are in hydrogen? We'll start with P plus equals N0 equals to give us the nucleus. The atomic number is 1, so that means there's 1 proton. The mass is also 1, so if the atomic number and the mass are both 1, how many neutrons are there? 0, because 1 minus 1 is 0. Remember, neutrons are mass minus atomic number. In an atom, the electrons equal the protons. So an atom of hydrogen is going to have how many electrons? Sorry? 1. So I put my first shell, I put my first electron in it, and we're done. Let's do another example for you. These 6 questions down here at the bottom, I'm going to skip this one for a second, I'll come back to it. These 6 down here, I want you to draw them all as atoms. And so I'm going to do nitrogen right here as an example. Nitrogen on your periodic table has an atomic number of 7. So I'm going to put P plus and N0 equals to signify my nucleus. If the atomic number is 7, that means there's 7 protons. And the mass is 14. So 14 minus 7 is 7. Means that nitrogen also has 7 neutrons in the nucleus. If it's an atom, it means the electrons are the same as the protons. So let's start drawing them. I'm going to put my first shell in here. First shell can only hold 2. So I'm going to put my 1. Now the thing is half full. So we're going to pair the next one up. There's 2. I've only drawn 2. I need 7. So I put my next shell down. I go 3, 4, 5, 6. I put 1 on each point on the compass. And now I start pairing them up. 7, and we're done. That's what the atoms are going to look like. So far, so good? Okay, let's look at the ions. Let's go back up here to lithium. We're going to draw a lithium ion. Now the atomic number, sorry, let's put this here first. P plus equals N0 equals. The atomic number on lithium is 3. So how many protons are there? 3. The mass is 7. So how many neutrons are there? Sweet, because 7 minus 3 is 4. The lithium ion, when it ionizes, it forms a charge of +1. So how many electrons then are there going to be? It's only going to be 2. So I put my first shell down there, half full, paired up, and I'm done. Because lithium is an ion, if it's +1, it has 1 less electron, so it's got 2. Put my brackets around there, put my charge of +1, and we're done. I'll do one more example of an ion for you. Flip the page when you're ready. I'm going to, on the top left-hand corner, I'm going to do the sodium, or the, sorry, top middle. I'm going to do the sodium ion. So always P plus equals N0 equals. The atomic number for sodium is 11, so that's the number of protons. The mass is 23, so that means there's 12 neutrons. And sodium as an ion is going to be +1, which means how many electrons is sodium going to have? Someone said 10. Good. Positive charge means you lost an electron. You have 1 less electron than protons. 11 minus 1 is 10. So first ring can only hold 2. Second ring, there's 3, 4, 5, 6. And now I've got to start pairing. 7, 8, 9, 10. And we're done. You put the brackets, charge up top, and there's your ion. Comments, questions, concerns? I should have. It should have been there. In my class, we never did. Did I make? I don't remember if I made you draw ions. Oops. Should have. Right. He did chemistry for you guys. Yeah. No, he should have. Okay. So that's it. For your guys' homework, I want you to do the 5 atoms on the previous page and the 5 ions on this page. Finish that up. You could get it done in the next 4 minutes before the bell goes. But that's what I want you to practice today, and that's the end of what we're doing. So if you got questions, let me know. Because it's lunch, I do want you to work to the bell. There's only a couple minutes left, so use this time. Don't pack up. On your mark, it's a giver.